Alright, problem one. There's no friction. Yay, it is accelerated. That's helpful. It wants me to find tension in the string, and all of my answers are given in terms of F, which is this external force. So I'm going to go ahead and rewrite the prompt and say this wants me to find T in terms of F, this external force. So what I'm going to do to simplify this problem, since this is going to ask for a variable, is go ahead and write the mass of each of these objects as m. So I'm going to say m and then 2m. And if I need to, I can say m is 1 kilogram in case for some reason I would like that. Also, I'm going to label the first block A and the first block B to make it easier for me to understand what is going on. And then I'm going to start drawing systems for each of these objects. Now, the reason why I'm going to treat each of these objects as their own system is because this wants me to find tension. And tension is something that is internal to the system A and B, as if this was one object. So I can't find the tension in this rope if I think about A and B as one object. Instead, I have to think about A as its own system and B as its own system. So let's just start with A and think of it as its own system. So system, then I'm going to label it A. Draw a free body diagram, and there are a few interactions with system A and some other objects or other systems. There is an interaction here at the surface, which usually would give me a resistance of friction, but this is a frictionless surface, so we don't need that. But there is still some force of support that keeps this block from accelerating through the ground. So that would be a force that is normal, or a normal force. Then there's an interaction with this block and the mass of the Earth, which we call the weight. So the weight would be going down towards the center of the Earth, and I'm going to go ahead and call this mg, since I know the mass of my system is m and the acceleration of gravity is going to be g. Okay, then there is only one horizontal interaction here, and that's the interaction between block A and the tension in this rope. So I would draw that off to the right, and I would call that T. Now, these two forces, the weight force and the normal force, are going to be equal to each other, but that's probably not going to be useful for this problem. If I want to think about the horizontal forces acting on the system now, it's kind of weird. I only have tension. Now, if this was a balanced situation, then tension minus something would equal 0. But instead, this doesn't equal 0. This will actually equal the mass of system A times the acceleration of system A. So that's Newton's second law. And if it's helpful for me, I can realize that this system of object A and object B, they are going to share the same acceleration. That is to say, the acceleration of object A will equal the acceleration of object B. So I can just go ahead and say that acceleration A equals acceleration B, and just say that that means the acceleration of the system. So this is a shared variable between each of these as their own system. So when I write the mass of system A, which is just m, and the acceleration as A instead of a sub A, I realize that tension in the rope is equal to the mass of system A times the overall acceleration of the system. Okay, but that gives me tension in terms of the mass of block A and the acceleration it's experiencing, but it doesn't give me tension in terms of F, the external force that system B is experiencing. So to look at that, we're going to think of object B as its own system, so system B. Then when we draw that object as a little point, there are a few interactions. There is the interaction with the surface that gives us a force of support that is normal, so normal force sub B. And then there is also going to be an interaction between system B and the Earth, the mass of the Earth. So that would be its weight force, and that would be the mass of the system times the acceleration due to gravity, or 2mg. There are two interactions to the right and to the left. There's some weird object, maybe it's your grandma or a cat, that is applying some external force. And then there is an interaction with the rope behind block B, so that would be the tension. And what's helpful is recognizing that these tensions, or the tension in the rope, is one and the same. So this is kind of that idea of Isaac Newton's third law, where the force is experienced by both objects. And normally we would just consider one object and not what the other is feeling. In this case, I realize that both of them experience the same tension. So these two things are going to be equal to two tensions. If I think about the horizontal forces acting on this system, I'm going to have the external force F minus whatever the tension is will equal the mass times acceleration of this system. So the mass of this system is mass B, and the acceleration of this system we could call a sub B. Now, I've already done this with the first problem, the system A, but I can go ahead and write this in terms of the actual mass of system B, which is 2m. And then I've already sort of realized that the acceleration of each object is the same, so I'm just going to call this A. So force minus tension is equal to 2m times the acceleration. So now I have two equations, and hopefully I have enough in these two equations to find t in terms of F. You probably like substitution, so the easiest thing to do would be to maybe figure out how to get rid of A, and the best way to get rid of A in each equation would be to rearrange this equation we got from system A as A equals t over m, and then taking that acceleration here and plugging it in so you get 2m times t over m. These m's cancel out, and you get f minus t equals 2t. Okay, so then I have f is equal to, if I add t to both sides, what I get is 2t plus t, which is 3t. And then when I want to find tension in terms of F, I just divide both sides by 3. And I realize the tension is equal to F over 3, which is option E on the actual problem. And I'm going to go ahead and solve this a different way, because there is an easier, less messy approach. These are two equations that share variables, so we can call these systems of equations, which is confusing because you're thinking of each of these objects as their own system, and that's not the same system. So if I have systems of equations, then what I can do is I can essentially divide both sides by what t is equal to. So what I'm saying here is f minus t divided by t. I'm dividing both sides of this equation by t. It's just that on the right side, instead of calling it t, I'm calling it ma, because that's what t is equal to. Now, if I do this, something funky happens. The mass and the acceleration cancels out, and I'm left with f over t minus t over t, which is just 1, equals 2. So then that means that f over t is equal to 3, and if I multiply both sides by tension and divide both sides by 3, then these two things flip-flop, and what I end up getting is that tension would be equal to f over 3, which again is option E, and that's what we're looking for. Now, this is not as messy as the other approach, but if you don't get it, that's okay.